Hello folks, welcome to part 2 of lecture 21 for our probability and statistics course. We begin now our final topic for this class, that of statistical tests of hypotheses. So we are going to begin with a number of definitions. We have to front load some notation and some definitions here, and we're going to do that today and also likely the first part of next lecture. So we are going to do this by maintaining sort of a running example as we go through and explore different concepts that come up in the context of statistical tests of hypotheses. So we're going to establish a running example here, and we're going to explore different ideas that arise as we move through this example and make definitions along the way. So suppose you are designing a vertical lift rocket capable of reaching orbit from the surface of the Earth. You have to be thrifty with mass because it's hard to get mass off the planet, as we've talked about. A supplier of bolts, or some other kind of basic component, is claiming that the average mass of their bolts is 4 grams. You do not wish to take them on faith. Instead, you would like to test this. So you want to do your own quality control on these components that you're obtaining from a contractor or a supplier. So you want to test this. A statistical hypothesis is a claim that is made about some population parameter. We will likely focus, I believe entirely, it depends on how quickly we get through some of this material, but I believe we are not going to see any tests that concern any population parameters other than mean. But there are statistical tests or statistical hypotheses that assert values for variance or mode or any other population parameters. For our purposes, at least initially, a statistical hypothesis is going to be a claim made about population mean, but you can have claims made about other population parameters. So for example, the manufacturer here is telling us that the average mass of these bolts is 4 grams. They are asserting a value for the population mean. They're claiming that mu equals 4. That is a statistical hypothesis. Hypothesis testing is going to be a means by which we determine whether we wish to accept, quote unquote, and we'll talk about the concept of acceptance in this context, but we are going to have a test of some kind, a means by which we determine whether we accept this statistical hypothesis or do we reject it. So we have to be able to test things somehow and decide, do we believe the manufacturer's claim that the average mass is 4 grams or do we not believe that? And when we say acceptance here, acceptance is always conditional when it comes to science and engineering. Even if a claim has not been yet rejected, if it has been quote-unquote accepted at some point along the process, your life or the world, like if a claim has been accepted to date, it's still subject to further testing. So really it might be better to say that we fail to reject the hypotheses or we reject the hypotheses. We never accept them, and they never become dogma of some kind. They're always subject to further testing. For the sake of convenience, people do talk about accepting the null hypothesis versus rejecting it, but it's just worth noting that it would be more accurate to say we either reject the null hypothesis or we fail to reject it. We have no reason to reject it at this point. So, as an example of such a test, suppose I decide I'm going to buy 100 of these bolts from the company, and I'm going to find the mass of each of those 100 bolts. And I'm going to decide to believe the manufacturer's claim if the average mass of those 100 bolts is between 3.5 and 4.5. So they're claiming that the average mass of all such bolts is 4, and I'm saying that I'm going to buy 100 bolts and I'm going to decide I believe them if the mass of those 100 that I buy falls within half a gram of the mass that they're claiming to be the average, 4 grams. And this is a fully arbitrary test. So this is not necessarily a good test. I just pulled these numbers out of the air. So we are going to talk more about how you would determine such values, like what are the cutoff values, what values would lead us to believe the manufacturer, and what values would lead us to doubt their claim. We're going to talk about how to find those values. So this 3.5 and 4.5 were picked arbitrarily just to indicate the nature of some kind of test, right? Like if I see the average mass of these 100 bolts close to 4, then maybe I believe the manufacturer. If I see the average mass of these 100 bolts far away from 4, then I no longer believe them. And here I seem to have defined close to versus far away from in terms of half a gram distance from the claim, and that was fully arbitrary. We will study more precise mathematical ways to decide what should constitute close and what should constitute far away. So I've decided to find a average of 100 bolts. I'll believe them if the average of those hundreds is within half a gram of their claim, and I will reject their claim otherwise. This is a statistical test of hypothesis. Again, it's not a great one because somebody just made up the numbers 3.5 and 4.5. In fact, I did. So it's not a good statistical test of hypothesis, but it is a statistical test of hypothesis. You have a criteria laid out which will determine whether you accept the claim that's being made, the statistical hypothesis, or whether you reject it. I slipped up there and almost said null hypothesis, and that is what the claim that mu equal to 4 is in this context. So the null hypothesis is generally the statistical test or the statistical hypothesis that is initially assumed to be true. So you're going to say, okay, there is some claim that's being made, let's assume it's true for now, and let's start to see whether or not the things that we see make sense. So generally there will be two statistical hypotheses associated with any statistical test. There's going to be the null hypothesis, which is initially claimed to be true, or assumed to be true, and then there's going to be an alternative hypothesis, which is what must be true if the null hypothesis turns out to be false. So the null hypothesis is a statistical hypothesis initially assumed true. And for instance, somebody working at this plant might say, okay, well, let's claim that we believe them, or let's assume that they're correct. Let's pretend that we believe this manufacturer. So let's pretend that we believe that the average mass of these bolts is actually 4 grams. Let's make some observations, and let's see how much sense these observations make under that assumption. That has some more of the spirit of how statistical tests of hypotheses work. If the things that we're seeing make sense under the assumption of the null hypothesis, then we have no reason to disbelieve it. But if the things that we are seeing do not make sense, if they are very unlikely under the assumption that the null hypothesis is true, then perhaps we reject it. We use h sub 0, known as h naught, so we pronounce that h naught to refer to the null hypothesis. And generally null hypotheses are stated in this way. You'll say h naught colon, and then you'll state the null hypothesis, which is here that population mean mu equals 4. So h naught colon mu equal to 4, that is the null hypothesis. The alternative hypothesis, as we said a moment ago, is what must be true if the null hypothesis turns out to be false. And so for instance, our rocket builders might say that if we see this sample mean for a sample of size 100, this average mass of these 100 bolts, to be either less than 3.5 or greater than 4.5, then we no longer believe the manufacturer's claim that the average is 4. And we use h sub 1 or h1 to refer to the alternative hypothesis. So h1 here says that mu is not equal to 4. h naught says mu is equal to 4. h1 says mu is not equal to 4. It could either be bigger than or less than 4. Alternative hypotheses in general can be what are called one-sided or two-sided alternative hypotheses. So a two-sided alternative hypothesis is just an inequality. So mu not equal to 4 without specification as to whether it is less than or greater than 4, simply that it's not equal to 4. A one-sided alternative hypothesis gives just a single inequality for mu. So we could say something like mu is greater than 4, mu is too big, versus mu is less than 4, it's too small. To think about this a bit here, like if we're manufacturing these bolts, when we're worried about mass, we don't want there to be too much mass. It's hard to move mass off the planet into orbit, and so we need things to stay less massive as much as we can. So generally, as long as the bolts still performed the way that they're supposed to, as long as they maintain their same physical strength and such, we'd be delighted if they weighed less. That would be wonderful for us. It would mean that it was easier to get our rocket up into orbit. Assuming that they're not flimsily made and going to break, right? So assuming that they have the same performance parameters, we'd be happy if they were less massive. Really, the problem for us would be if mu was greater than 4. If the average mass of these bolts turns out to be larger than was claimed, then we would have issues. And so it makes sense that in certain contexts you would want to think about one-sided alternative hypotheses instead of two-sided alternative hypotheses. If you're budgeting for the month, for instance, it's not a problem if you have too much money at the end of the month. It's a problem if you run out before the end of the month. So lots of times there's sort of a one-sidedness to certain problems that you're concerned with. That being said, we are going to focus on two-sided alternative hypotheses for the remainder of the course There's not a great deal that has to be done or adapted to get from the two-sided to the one-sided, but for the sake of doing a thorough job with the fundamentals here, our focus is going to be on the somewhat simpler mathematical case of the two-sided alternative hypotheses. Again, by the end of the course, you will be well equipped to teach yourself the material for one-sided were you to need that. So our next definition is that of a test statistic. The test statistic is some statistic that you will use, and remember that a statistic is a random variable defined in terms of a sample. So you're getting a sample and you're computing some number from that sample. And this is the number that's going to determine if you accept or reject the null hypothesis. For us, the test statistic was a sample mean for a sample of size 100. That is our test statistic. Depending on what that value turns out to be, that's going to decide whether we accept or reject the null hypothesis. The test statistic is a way of summarizing the data that's contained in a sample that you have observed. And our test that we have laid out is going to define the collection of all possible values for the test statistic into two different regions. So you're going to have a critical region, which are those possible values for the test statistic which would cause you to reject the null hypothesis. And you will also have an acceptance region, which is that collection of possible values for the test statistic which would lead you to accept, or rather would give you no reason to reject the null hypothesis. So the acceptance region and the critical region are going to be, your test statistic is going to fall somewhere on the line, right? Here this is a one-dimensional statistic, so it falls somewhere on the real line. There's a portion of values on the real line, for us it's between 3.5 and 4.5, where if your test statistic happens to land in that region, you have no cause to reject the null hypothesis. If your test statistic falls outside of that region, in the critical region, that's when you reject the null hypothesis. So the intuition here is that we are assuming the null hypothesis is true. Under that assumption, the critical region are those values that don't seem likely for the test statistic. So if we assume that the actual mean mass of these bolts is 4, and we take the average mass of 100 and find that to be 7.5 grams, that seems ridiculous. If the true average mass really is 4, it doesn't seem likely that these 100 that we bought happen to have average mass of 7.5. So 7.5 falls in the critical region for this test for those reasons. The critical region is composed of those values which, under the assumption that the null hypothesis is true, would be particularly unlikely. Whereas the acceptance region is going to be those possible values for your test statistic which are pretty reasonable under the assumption that the null hypothesis is true. So if the null hypothesis is true in our example and the average mass of the bolts really is 4, then it doesn't seem surprising to us to see a value that's near 4 but not exactly equal to 4. We said between 3.5 and 4.5. So those possible values for our test statistic are relatively likely. They're unsurprising under the assumption that the null hypothesis is true, and if we observe such a value, it gives us no reason to doubt the null hypothesis. That's the idea here. And as a final definition, the critical points for such a statistical test of hypotheses are the boundary points between the acceptance region and the critical region. So for us here, the acceptance region is the interval from 3.5 to 4.5. The critical region is the rest of the real line. So everything less than 3.5, from negative infinity up to 3.5, not including 3.5, and everything greater than 4.5. So from 4.5, not included, up through infinity. That's the critical region. If we see an average mass of the bolts anywhere in that region, then we reject the null hypothesis. A quick-witted reader or follower along of this lecture, I should say, might notice that there are negative values involved. If we find a negative mass of these 100 bolts, then we should start to doubt our own sanity, or at the very least, the equipment that we're using to take these measurements. But for the sake of simplicity, I have not included that here. I'm just saying everything except everything outside of the acceptance region, the complement of the acceptance region, if you will, is the whole of the critical region. It would be fully reasonable to say from 0 to 3.5, and then from 4.5 out to infinity. The critical points here are the boundary points between these two regions. So where do you go from one to the other? It's right at 3.5 if you're moving left to right. You jump out of the critical region and into the acceptance region as you pass through 3.5. and you jump out of the acceptance region and back into the critical region as you pass through 4.5. Those 2 points are the boundary points between these 2 regions. So finally, in this running example that we have been discussing, we have a null hypothesis that mu, the population mean, is 4. We have a two-sided alternative hypothesis that mu is not equal to 4. We have a test statistic that we're actually going to compute based on a sample, and for us here it is the sample mean from a sample of size 100. We have an acceptance region, 3.5 to 4.5, that interval, such that if our test statistic falls in that acceptance region, we believe the null hypothesis. We have a critical region from negative infinity up to 3.5, and then from 3.5 to 4, with those boundary points not included, which, if our test statistic falls in that region, we reject the null hypothesis in favor of the alternative hypothesis. And finally, we have critical values. Those are the boundary points between our acceptance and our critical region, and they are 3.5 and 4.5. So the next topic that we are going to discuss in the first part of our next lecture is going to be types of error. So associated with such a statistical test of hypotheses, there's different kinds of mistakes you can make. And these are largely going to be definitions, but they're such important definitions that we want to give them their own separate consideration. In particular, just as a preview of what we will discuss next, it's possible that my null hypothesis turns out to be true, but that my test causes me to reject it. So maybe the mean mass of these bolts really is 4, but the 100 that I get happen to be particularly heavy, so that their average mass turns out to be, say, 4.7. My test is going to instruct me to reject the null hypothesis when in fact the null hypothesis turned out to actually be true in that case. And that's going to be what is known as a type 1 error. A type 2 error is going to be when the null hypothesis is actually false, but your test of hypothesis leads you to accept it. So rejecting a true null hypothesis is a way to make an error, and accepting a false null hypothesis is a way to make an error. And those are called type 1 and type 2 errors respectively. We're going to consider them, and the way that we ultimately come up with the actual critical values, the actual boundaries of our acceptance region, is going to be considering how likely are we willing to allow these different types of error to be. Generally, if you want to decrease the likelihood of one type of error, you have to allow an increase in the likelihood of the other type of error. And based on a consideration of the real-world ramifications of making those two types of errors and our tolerance for risk of making each of those types of errors, that is going to determine what the boundaries of your acceptance region are, what your critical values are. So here I just pulled 3.5 and 4.5 out of a hat, but we're going to see that by considering the different types of errors and by considering the likelihood of making the different types of errors, we can determine what those points, those critical values, should actually be. All right, I thank you folks. We will speak again shortly.